So our next speaker is Dr. Krste Asanović. I'm sorry, I'm killing your name. Asanović is a professor in the EECS department of the University of California, Berkeley. He received his PhD in computer science from UC Berkeley in 1998. He joined the faculty at MIT, receiving his tenure in 2005. He returned then in 2007 to Berkeley and co-founded the Berkeley PAR Lab, the Parallel Computing Laboratory, has led the Aspire Lab and co-led the ADEPT Lab. His main research areas are computer architecture, VLSI design, parallel programming, and operating system design. He currently is the co-director of the new Berkeley Slice Lab, and which is improving specialized computing in ecosystems, and is an associate director of the Berkeley Wireless Research Center. He leads the free RISC-V ISA project at Berkeley, is chairman of the RISC-V Foundation, and is chief architect and co-founder of SiFive. He is an ACM fellow and an IEEE fellow. Join me in welcoming our next speaker.
Okay, good morning, Dallas and everybody online. Thanks for inviting me to supercomputing. I'm very excited to come here and tell you about RISC-V and what it can do for high-performance computing. So I thought I'd start off with explaining what is RISC-V, then why it's inevitable and why this is going to be good for high-performance computing. So how many of you know what RISC-V is? Great. How many of you know that it's an open source processor? Okay, you're all wrong. So RISC-V is not an open source processor. So that's why I do that spiel, and I'll go through and explain what actually is RISC-V. Now I want to talk about why it's inevitable. This is a phrase Dave Patterson coined, but I'll go through why it's inevitable and why this is actually a good thing for high performance computing. So in the computing industry, we have open standards, and that's accepted practice almost everywhere in the computing stack. So look at networking, we have Ethernet. Ethernet's an open standard. You build a network. If it's not Ethernet, everybody's going to give you a pretty funny look. Why isn't you using Ethernet for your networking? Right? And because it's an open standard, you can have free and open implementations of it, but you can also have proprietary implementations. And going through the computing stack, even including APIs, things like POSIX, or graphics programming languages, or other forms of standards, Wi-Fi, 5G, open standards are the normal way the computing industry does business. But for some reason, the most important interface, where software meets hardware, the instruction set, up till now, we haven't had an open standard. We have proprietary interfaces, like x86, ARM, or the grandfather of them all, IBM 360. So why haven't we had this? And this is a problem. You may say, well, who cares? The problem is the companies that own these ISAs, they come and go repeatedly through history. So some examples, there used to be a very big, important computing company on the East Coast called DEC. And they had very important ISAs like PDP, VAX, and Alpha. Alpha was, the darling of the high-performance community during the 90s. But it disappeared. Why? Because it was a lousy instruction set? No, it disappeared because of the business mismanagement at DEC or whatever. They went out of business. Intel has also, promoted a lot of ISAs, inflicted titanium on the community, right? That's gone now as well. Spark, one of the early RISCs, classic ISA. Now, we need to give some credit. They actually made it an open standard with the IEEE back in '94. And there was a lot of companies making Spark processors. But at some point, and that was a 32-bit Spark, at some point they were acquired by Oracle, and Oracle closed down Spark in 2017. So it's a dead ISA, it's gone. So any code you have, any supercomputers that's still based on Spark, that's a dead ISA as well. MIPS. MIPS was another one of the classic RISC ISAs. A lot of development around MIPS. You might remember SGI, very important in supercomputing at one point. Went through some pretty bad times. They were sold to Imagination, then bought by a startup Wave, which is also closing down. So after RISC-V's success, at some point they opened up MIPS R6 in 2018, but then the next year they closed it down again. Now MIPS actually is making RISC-V processors, right? IBM Power, so another important ISA in the supercomputing space, was proprietary. They sort of opened it up in 2019, but you really don't see people doing much with the Power ISA, an open Power ISA, right? ARM, so ARM is a pretty important ISA in the industry, but there was a lot of shockwaves in the industry when SoftBank acquired ARM, took them private in 2016. People wondering what's going to happen there. And then there was even bigger shockwaves when NVIDIA announced they're going to acquire ARM, or trying to acquire ARM in 2020. That deal got shot down because it was viewed as anti-competitive. And now the company's seeking an IPO, which is also causing some interesting behavior on their part, which is getting people excited. So the real point of this slide is to say, why are we entrusting our software investment to a proprietary ISA, right? They come and go. And a lot of the work is in targeting the actual ISA of your machine, right? So why can't we have an open standard? The second problem I want to address, the first one there being proprietary ISAs, the second one is what I call ISA Balkanization. If you look at a modern system on a chip, it's not just one ISA on that chip. There are many components, a modern SoC. This is actually quite an old SoC, but it illustrates the point. You have the applications processor, which is what most programmers see. They think, oh, this is an ARM chip. It has an ARM applications processor. Yes, it does, but it also has graphics, image, radio, audio, security, power management, many other processors on that chip. And it's not unusual to find over a dozen different instruction sets on one chip. And each of those has a unique software stack. And usually most of the software stacks are pretty lousy because it's a little niche area. They don't have time to invest in the software for that. So why does this happen? Well, a few reasons. One is, even if you could use the application processor ISA everywhere, it's too big and bulky and not designed for those embedded applications. So you don't really want to use it there. Second, though, it's proprietary, so you're not allowed to use it in these other blocks, even if you wanted to. So what happens is, when you build these SoCs, you assemble IP from lots of places. Each of those places, they're not allowed to resell, for example, they can't use the ARM ISA as the basis of their IP. That's just not allowed. So they have to do their own ISA. So then that's where the proprietary ISAs come from, right? Another reason this happened, and this is the worst reason, is engineers design their own ISAs, right? So if you're involved in any project anyway, do not let people design their own ISAs. It might look fine. They've taken, you know, Dave Patterson, John Hennessy's class. They know how to port GCC. They think they can build an ISA. It kind of looks good the first time, but then you realize you have to support software in this ISA. Then you realize all the things you did wrong and just the extreme effort it takes to support software, right? So don't do that. But this is the problem. You have many ISAs on a single chip. Most of the ISAs are ill-supported with software because there just isn't enough investment possible for the market of that particular core. So do we need all these different ISAs? Do they have to be proprietary? Do they have to keep disappearing? You know, so the premise of RISC-V is, what if we had one stable, free and open ISA that everybody could use for everything? And that's basically the idea behind RISC-V. So just the background on RISC-V, it started back in 2010 when we were doing the Power Lab at Berkeley. And we just needed something for our research projects. And the obvious choices would have been x86 or ARM. But x86 was just impossibly complex. You know, we were a bunch of grad students wanting to build cores. It would take forever if we had to base it around x86, right? ARM, it turns out, was almost as complex, not quite as bad. But back in 2010, there was no 64-bit ARM. We wanted to do work with 64-bit address spaces. ARM v8 only came out in the following year, 2011. And for both of these ISAs are IP issues. We wanted to build infrastructure, share it with our colleagues and other academic institutions or the industry collaborators we had, but that's impossible with those ISAs. You're not allowed to build your own core and give it away for these ISAs. So we started a project to do our own ISA. I'll give a shout out to the major designers, Andrew Waterman, Yunsub Lee, as well as Dave Patterson. But a lot of people helped along the way. Many other folks contributed. And we thought it would only take 3 months. But 4 years later, we finished the base spec, so it took a bit longer than we thought. But we didn't just sit around pontificating about ISA design. We actually built several chips. We ported compilers, we ported operating systems, and iterated around for a few years. To around 2014, we thought it was pretty good and worth, you know, putting out there. The name is RISC-V, not RISC-V. It's in Roman numeral, so it's RISC-V. And it follows the naming of the other earlier RISC chips. So RISC-1 and RISC-2, you notice they were not called RISC-I and RISC-II. So it's RISC-V, not RISC-V. Now, one difference with RISC-V versus the earlier designs was RISC-V was designed as an architecture, not just for one chip. So the first chip was actually back in 2011. It was in 28 nanometer FDSOI. It was a 64-bit core, a simple core we built. But that was only the first of many, many other RISC-V implementations. It was always designed as an architecture, not the ISA of one chip. So by 2014, we feeling pretty good about this. It got a lot of interest from outside. We decided to go to Hot Chips, major conference, and we all wore these blue T-shirts. I've still got mine. That's what I'm wearing here. And made a big splash, tell everybody about RISC-V. And we had a very positive reception. A lot of folks in the industry were like, this is what we want. We need something like this. This is great. But one thing they also told us, it cannot stay a university project. It has to be well supported and become a stable thing for us to invest in it. So then we created the RISC-V Foundation, which was a nonprofit entity to manage the standard. And this is now morphed into RISC-V International, based in Switzerland, which is a global standards organization managing this standard. Now there's several thousand members of RISC-V International, many companies and organizations around the world working on the specs. So how does RISC-V work? Well, first, this is just an eye chart of all the many participants in RISC-V. Nearly all the major companies in the computing industry are involved. And recently Intel joined, as some big news this year. Intel joined the RISC-V Foundation and pledged a huge chunk of money to help develop the ecosystem. So how does RISC-V work? Well, RISC-V International sits at the middle and manages the specifications, the standard for the instruction set. And that means the specification, the go-to model as a formal model, and the compatibility suites. So it's important to note RISC-V is an open standard. It is not an open source processor, right? But because it's an open standard, defining this interface between software and hardware, it means you're allowed to have open source processors. And there are many open source RISC-V processors. At last count, well over 100 are available to go download from various places. But it's not only open source. There's a lot of commercial core providers. So these are companies with the same business model as a company like ARM, for example, where you go license a core, you pay a large amount of money, and you pay royalties on using those core designs in your chip. A very conventional commercial core market. One thing I'll notice, there are more RISC-V core IP providers than there's ever been for any other ISA ever in history, right? It's a global phenomenon. There's many companies providing RISC-V cores already. As well as that, another option some companies take is they build their own RISC-V cores in-house. They don't intend to sell the core separately. They're not using an open source core. They have a team that builds their own core for their own uses. So for example, NVIDIA, all their GPUs use RISC-V to control the GPUs. It's not visible to the programmer, but all the control functions of the GPU are now done by RISC-V, and sometimes there's 10 to 30 RISC-V cores on a GPU. Seagate, Western Digital, highly motivated, the disk controllers are their own RISC-V cores driving those parts now. As well as these, there's also commercial silicon providers, folks who are building silicon to sell that's based on RISC-V. And there's many of these in a growing number. Some of these are startups. Some may have disappeared by the time, between the time I did the slide and now. But there's an ever-growing group of companies providing RISC-V silicon. So that's the hardware side. And the good thing here is that hardware side all obeys the same interface and so can leverage the same software stack on top. So on the software side, we have a very big footprint in the open source ecosystem. Open source developers like the RISC-V ethos. There's a very big and growing set of standard open source upstream projects that target RISC-V, things like GCC, LLVM, Linux, and so on. But again, it's not only open source software. There's a big commercial software side to RISC-V too. So companies like Lauterbach, Sega, Wind River, Green Hills, these are folks who sell expensive tools and licenses that you have to pay for, but they're supporting RISC-V because there's demand from their customers who are using RISC-V in their projects and expect to see the same professional tools that they used to with RISC-V projects as well. So again, RISC-V is an open standard. It's not an open source processor, but because it's an open standard, it enables there to be open source processors, right? Now, where is RISC-V? A lot of people are like, where are the chips? Well, estimates this year, something like 10 billion chips shipped with RISC-V on there. So 10 billion. So it's shipping in mass volume. A lot of the applications are things you do not see it as being a RISC-V core. It's buried away in some embedded device. Predictions from independent analysts are something like 60 billion cores will be shipping by 2025. And I think this is actually quite a conservative underestimate. Not everybody is saying what they're doing with RISC-V. But there's a lot of cores out there, so it's not a future thing. It's here and now and shipping in vast volume commercially already. But so far, mainly in embedded applications. Education, it's spread widely in education. It's very popular. It came from education. The great thing is we can have complete RTL designs of a core and ship it to students, and they can play with it in the labs, right? Plus all the software is there. So it's very easy to use and a great thing for education. So, Patterson and Hennessy, they've updated their undergrad and graduate textbooks to be based on RISC-V now. So now we have literally tens of thousands of undergrads every year learning RISC-V through their classes. Okay, so that's a quick recap of RISC-V. Now I want to sort of go over why is it becoming popular from the business side. And I'll start out from the big change that's happened in the last few years in the semiconductor industry. These days, it's primarily a vertical model, whereas previously it was a horizontal model. What do I mean by that? So what I mean is when you're a product company, instead of buying standard parts to make your product, the most advanced product companies, they build their own silicon for their own products. So they want to differentiate the capability of their product by building custom silicon for that product. And you see that companies like Apple and Amazon for wearables, TVs, phones, laptops, the cloud, the hyperscalers building their own server chips, Tesla building chips for their own cars. So the point here is they're building these chips not to sell chips, but to sell phones, cars, cloud services, right? And this changes the economics because they don't have to worry about, can I make money selling this chip? Can I make money selling an iPhone? And that really changes the economics of when you can build a custom chip. If it's not about a chip sale, but it's about a much higher value product, right? So this verticalization is a big deal in the industry. And you've seen the supporting industries adapt. So this is why there's such success. TSMC has been such a success, right? They're an important, crucial part of this model of these vertical teams doing everything from the product design, the application, the coding, hardware, all the way down. This is hardware, software, co-design at industrial scale that's going on right now. And so the industry is designed to support these teams building these chips for particular products. So this is the current vertical semiconductor model. Companies that are used to the standard parts model are in trouble because of this. They're having to realign to the new reality of what's going on in industry. So why is RISC-V so popular? A lot of you are very technically minded. You came in a technical track, you're a supercomputing. But I have to remind engineers that sometimes you don't see the forest for the trees, right? So RISC-V isn't happening because something is 10% lower power, or 30% faster, or whatever. That's not why it's happening. The reason happening is a new business model, right? So previously, the way it worked, you're building one of these SoCs, you first had to go to a vendor, and they would give you a core with their ISA. This is flipped now. So first you say, I'm going to do RISC-V. Then you have multiple vendors competing for every socket that you want. And this changes everything, right? So now there's no lock-in, I get competition, and I get a lot of freedom. The other freedom you get with RISC-V is you can add extensions. You can customize the ISA without getting permission, unlike the other standard ISAs. And now this means you have commercial, academic, open source ecosystems. They all coalesce around the same open standard, right? And this is very powerful, and this is why RISC-V is getting popular. So again, to explain business models, I put this slide together because I had a lot of questions. I understood there's a lot of confusion with folks about how these different ones work. These are not really comparable because they have different business models. x86 ISA is only available through a microprocessor business model. You cannot get a soft-core x86 and put it on your own chip. You have to go to Intel AMD. They're the only ones who are allowed to make an x86 chip, and that's the only way they sell them. Now, you can ask them to make you a custom chip, like a games machine from AMD, for example, using an AMD chip. But they're the only ones who make chips using that core, right? So it's a very different model. So there's two vendors from which you can get x86 silicon. That's the business model. That's it, right? You cannot get an architecture license to build your own x86. There's no commercial core IP you could integrate on an SoC you build yourself. Can't add your own instructions, and there's definitely no open source core IP, right? That's x86. So that ISA has this particular business model. ARM is quite different. ARM is licensable. There's many chip vendors who sell chips. You can get an architecture license, which allows you to build your own ARM core, but it's expensive and it's restrictive. You can build your own ARM core, but you're not allowed to sell that IP to somebody else. You can only use it on your own silicon. Okay, so if you're Apple, yes, I have an ARM architecture license. I build my own ARM cores. They're only available on Apple chips inside Apple phones or laptops. Okay, they're not available to anybody else to use. Can you get commercial core IP? Yes, but only from one vendor. There's one place you can go to get a licensed ARM core, and that's ARM. Can you add your own instructions? Mostly no. In response to some RISC-V pressure, some of the embedded cores, they started to allow you to customize a little bit, but basically no. Open source core IP? No, definitely not. So RISC-V, different model, open standard. Chips, yes, many vendors. Architecture license, yes, everybody can download the spec and go build something that's compatible with the RISC-V ISA. You don't have to pay anybody anything or to tell anybody you're doing it. Is there commercial core IP? Yes, there are many vendors selling you commercially verified, guaranteed, supported, possibly expensive IP available. Can you add your own instructions? Yes. Is there open source core IP? Yes, there's hundreds of cores available if you want to try using open source cores. So these are the big differences in the business model of different ISAs. So, I grew up in the UK, and in the 80s, there was a bank who had a famous advertising campaign, so I stole their tagline. RISC-V, it's the ISA that likes to say yes. Yes, you can do that, right? Now, if you think about the vertical design teams again, why do they like RISC-V? Well, all the cores in the SoC can be RISC-V. Everything from the main apps cores down to the microcontrollers can all be RISC-V. They can choose different vendors for each core, but they're all RISC-V. Common software stack and tools. You can customize the RISC-V cores for specialized tasks. So you can build an audio DSP based on RISC-V. You can build a vision processor based on RISC-V. You can build a power management core based on RISC-V. And this gets rid of that SoC ISA Balkanization that currently exists in these vertical designs. So I just wanted to give one example of a project. And I thought this would be interesting to this crowd because it's a collaboration between SiFive, company I founded, and Google on the next generation TPU, the high-end training machines. So we presented this at the AI Hardware Summit a couple months ago. So I'm going to dive into some SiFive product stuff, but I'm actually wearing my RISC-V Foundation hat primarily today, but I can use this because I have the slides and it's a good example. So one of the SiFive cores you can license is a core we call the X280. It's what we call an intelligence core. It's designed for this point when you want reasonably efficient scalar processing, but a big vector unit to do number crunching. So it has a 64-bit scalar unit, full RISC-V ISA support. It can run Linux. It can run a hypervisor, full application core capability, but has a wide vector unit that's fully RISC-V 1.0 spec compatible. It has 32 512-bit vector registers, very capable core, but quite efficient. It's a dual issue in order core, but with a wide vector unit on the side. Has an efficient memory system. The vector unit goes directly to the L2 cache to improve throughput and to give it a larger working set. It's called Intelligence Core because we added a few extra custom instructions to help with AI. And our original goal for this was customers who needed a reasonable size core to go in edge devices to do some AI work as well as regular number crunching and just regular app processing. So this is the X280. So just to explain a little bit, so if you this is just one application example on the X280 running an inference task, mobile net. Just using RISC-V vectors, we got a big speed up, 24x. What you would expect, going from a simple in-order processor to using wide vectors on a dense problem like mobile net, 24x speed up. But in addition, we added some extra matrix multiply instructions inside the core. There are SiFive custom, and we get another 6x speed up on this task using those. Okay. But this isn't really enough. If you're serious about AI, this is nowhere near enough computing. You need a really big engine, right? And what surprised us when we started selling this was, first of all, we started selling it a year ago, and big uptake. A lot of customers were licensing it. We're trying to figure out why. We're very happy, but why are they buying this? We realized one of the big use cases was a companion core. So a lot of companies had built a big AI accelerator, this very capable hardware engine that could do matrix multipliers really fast. The thing they'd forgotten about was software, right? So, it's no good having this big engine without software to run on it. And they built some little thing around it and realized they needed some companion core to basically run most of the software stack and drive their accelerator. And we had a lot of sales in this category, and we're like, what's going on? Then we realized this is what was happening. But the initial design of the X280, we just had a memory mapped interface. You had to connect it over a memory bus, and that's kind of slow and painful to talk to an accelerator. So working with some of the customers, we added what we call the vector coprocessor interface extension. Basically, you can take your accelerator and plug it into the vector registers. So now you can ship vector data in and out of the vector registers directly to the accelerator. So you get down from sort of 100 cycles to get across a memory fabric to maybe 10 cycles, just the latency through the vector unit and the functional units. So some customers are using this just to add extra instructions, particular FFT or some kind of matrix op, but others are using it to drive their accelerators. So there's a bit more detail. So this sort of sits in right next to the vector registers. As well as supplying data, we can also send custom instructions. So RISC-V divides the instruction set into standard instructions and custom instructions. And it's guaranteed that if you stay in the custom encoding space, anything you add will not stop the standard software from running. So you can have Linux, hypervisors, whatever, and on the side you have your custom extensions. And those instructions live in the same instruction stream as the regular RISC-V code. And so as you're running this code, we can be shipping those instructions off to the side to your coprocessor alongside vector data, and it's all interlocked with the regular vector instructions, so you can send data over, then do a vector operation, the vector registers on that data when it comes back. So that was how we designed this VCIX. So as I mentioned, we've been working with Google, and they publicly disclosed this at AI Hardware Summit. So they've been looking at their TPU design. They've gone through several generations. And basically, the TPU unit is a big matrix engine connected to high bandwidth memory, plus some vector and scalar processing units. And what they kind of realized was the only things that they really did that was unique was that big matrix engine and some of the interconnect to the memory system. And the big problem they were having is supporting the software for the thing they built to drive the TPU. It was just cumbersome and it wasn't really effective. Like one example Cliff pointed out was, well, to do memcopy, I actually have to do a matrix multiply. The only way I can copy memory is by sending it through the matrix engine. Kind of example of the difficulties they had. So and these slides are from Cliff. So the way they view the world is SiFive builds the X280, which is a full RISC-V core, full software support, including vectors. Google focuses on the matrix multiply unit, and there's this tight coupling. So, it's a nice division of labor. They get to build a high performance engine, but get the full software stack, and all the ancillary processing can be done on that X280. Right, so this is just one example of RISC-V being used in high performance market to provide customization. But I want to also highlight RISC-V is not only about embedded and customized cores. There's a lot of work going on in high performance application cores, like general purpose processors. So I happen to be at SiFive, so this is the example I have. So the P670 was just announced. This is a high performance out of order core, quad issue out of order core with vector extension, hypervisor, coherent multi-cores up to 16 cores, security, sophisticated trace and debug, all the kind of features you want in a high-end applications core. This performance point it's roughly about the performance of a ARM Cortex A78, but it's about half the area and half the power. So significantly more efficient than the ARM core of equivalent performance. It's just a slide to show you it has all the things you would expect to find in an out-of-order applications core. But SiFive is not the only one doing this. There are many other high-performance RISC-V vendors out there. So I listed some of them here: Alibaba, Andes, Esperanto, Riva, Semidynamics, SiFive, Tenstorrent, Ventana. There's probably a bunch more, and I've lost their names. So a lot of companies are developing high-performance RISC-V cores, and these are all superscalar, out-of-order, vector-capable application cores. Okay, so this slide is actually my public service announcement for you all. Obviously, I'm heavily biased and conflicted, but I want you to take this in the spirit of a public service announcement about RISC-V. So it's inevitable, right? So just think about Ethernet or think about Linux. This is what's happening with RISC-V. And the reason is nothing technical. The reason is industry wants this business model. It's very simple. They want an open standard ISA. So that's number one reason why it's happening. Now, this wouldn't happen if it was a lousy instruction set, but thankfully, it's actually pretty good. So what this means, RISC-V is going to have the best processors. The ISA looks like it comes out better than the others when we do the evaluations. And there's more vendors competing with more cores designed for RISC-V. There's much more competition, and that'll help the quality of the processors that become available. And because of this, it's also going to have the best ecosystem. right? There's the largest number of players. All sockets will eventually become RISC-V, and software wants to run the best processors available. Now, obviously, I'm very biased, and you can just say, well, obviously he would say this, but I honestly believe this, and I do take this to heart. This is what's going to happen. I don't see any reason why this would not happen, right? So this is the future. This is what's going to happen. So, we've been getting these results on our cores against competing cores, and our customers have been asking us, because they're the ones that do the evals. They take our IP, they take competitors' IP, they compare it, and they're asking us, how come you are half the area? And so we're like figuring out what's going on here. And as we dive in, there are definitely some technical benefits to RISC-V. Much reduced dynamic code size. You have a compressed instruction set. People said that would hurt your performance, but it doesn't actually. If you know what you're doing, you can use it to improve performance of the same area. We have a compare and branch instruction, very trivial thing. The other major ISAs have a compare and a branch. Branches are pretty common in code. The other architectures have to fuse those. That adds complexity. ARM instruction set, integer has to have 3 read ports. RISC-V, we made it only 2 read ports. Sounds small, but all these things add up. There's a lot of small details that seem to be adding up to why we seem to have an inherent advantage at the ISA level. We have the advantage of a clean design as well. We avoid a lot of the legacy warts from the other architectures. Now, one thing that will be important for HPC is we designed from the beginning to have a variable length instruction. And although this goes against classic RISC principles, the reason was kind of clear to us that you cannot fit all the instructions you need in a single 32-bit word. And all the other ISA vendors have discovered this. So ARM has to have a prefix instruction to use their vectors. IBM similarly had to add a prefix instruction to use their vectors. They actually have a variable length instruction set. They're just pretending they don't, right? You need a variable length instruction set to provide a full vector feature set. The other big advantage is community design. So there's many people contributing to the ISA from all across academia and industry. Folks who built the ISAs at Intel, ARM, other places, they're contributing to the RISC-V design. And because it's an open forum, an open discussion, you get the best ideas of winning in the overall design. So there's basically no limit to the performance levels or applications people can use RISC-V. And it'll basically, prediction is like 2 or 3 years we'll be surpassing the other architectures in available performance with the designs that are in flight right now. Okay, so I talked about what is RISC-V, why is it popular? How about RISC-V and high-performance computing? Well, the Google was one example I gave. But I think the number one reason it's a great match is it's a stable, long-term platform for software. So the most important part of a high-performance computing system is the software, right? And Bill talked about 40,000 lines of code for a code. That's like nothing, right? The Google guys are worried about the 40 million lines of code they have to run on the X280, right, to get Linux up and all the apps and that environment that people want. So the important thing is you need stable, long-term platform. RISC-V is a global standard. It's not dependent on any vendor. Even if SiFive gets bust or acquired, it's not going to make a difference to RISC-V. It's independent of any one vendor. That's part of by design, right? So it's a global standard. It's not going away. We even have a 128-bit address-based version in draft form because we're going to need that by the end of the decade, right? We're going to need more than 64 bits of address space by 2030s, right? So that's already built in to the plan. So it's a stable, long-term platform. You will have to port software, but this will be it. Like, that's the idea. This will be the Ethernet of computing is RISC-V, right? Now, the good news is it enables very efficient scalar processing. Very important for HPC. You have to run scalar code very well. Crane knew this when he built the Crane 1. We also have very efficient standardized vector processing as well in RISC-V. We have a very clean vector length agnostic vector architecture. Many people are implementing it, seeing advantages over the other vector architectures. It also enables these tightly coupled custom extensions while staying compatible with standard software. So this is great for HPC apps where you need a certain kind of accelerator or engine. You can add it to RISC-V, but stay compatible with all the other software. You don't have to break your whole universe just to add a widget to do graph processing, for example, right? Now, it's still early days for RISC-V and HPC. To give you an honest equivalent analysis of the status, and the thing people have to realize, from when a core design is started, and you build the IP for the core, to when that's integrated into a chip, and the chip then goes through physical design, then it gets fabricated, then it gets qualified, then it gets put on a board, the board gets qualified, then it gets deployed in a rack. That takes years, multiple years. There's a lot of products in the middle of that pipeline right now. So it can seem like, well, there's nothing there, right? But there's a lot of stuff in the pipeline that's appearing. Now, in terms of software support, auto-vectorizing compilers, vector intrinsics, math libraries, these are still immature for RISC-V vectors, but they're advancing rapidly. A lot of people are working on this and trying to push this along. HPC software stacks, also going to take time to port. We need a lot more available hardware to help people bring up those HPC stacks. So I do want to give a shout out to the team from Barcelona, the UPC team there. And they were the audience favorite at ISC because they built a small cluster of these SiFive development boards, these unmatched boards, and they're starting to bring up HPC stacks on these boards. Now, the way you should look at that is you should remember the early Beowulf systems, right? That's kind of what this is. It's that same early look at what's going to be normal later, right? Just a few boards there, not very capable boards. They're just software development boards, but they're starting that process of bringing up the software, right? Some more news on development boards. One thing I should also mention is we had a little problem with development boards. Like everybody else, the pandemic hit supply chain, so those unmatched boards, we had to stop making them because we could not get power supply parts for them. We redesigned the board several times. We gave up because we couldn't get parts. So there's been kind of a lull in available boards for the same reasons as a lull in everything else these days, right? But hopefully coming soon, we'll have the next generation dev board. Intel is putting together a dev board based on Horse Creek chip, which it's in Intel's 4 process technology. So this will actually be the first processor in Intel 4, even before an x86 shows up. It is just a dev board. Don't get too excited. So it's a quad-core SiFive P550, so it's a 3-issue out-of-order superscalar with 8 lanes of PCI Gen 5 and DDR5 memory systems. This will be showing up sometime soon. Stay tuned. So just want to recap, and I want to leave some time for questions. So again, my public service announcement, RISC-V is inevitable, right? And that's good. It's a good thing for HPC. It's going to provide a very stable and efficient base for all future HPC systems. And when I think about where RISC-V fits, if I go look back at the dominant instruction sets, they all fit a certain time and place in history. So the IBM 360 was the first instruction set architecture, and that was really IBM realizing they couldn't afford to maintain software for 4 different product lines. They had to merge them into one ISA and just do different implementations, and having to coincide with transistors becoming the dominant way of building machines. So the 360 really dominated that transistor era. When people started making microprocessors, getting the whole processor on a single chip, basically x86 ended up dominating that era of design, the microprocessor era, where you buy a piece of silicon with a processor on it, and then do board-level integration to make your different products, right? ARM really became successful in the mobile era, where companies needed to put a lot of different IP on a single chip to make a viable phone, and the IP included modems and graphics and other things. And they didn't want to design the processor, so ARM figured out how to sell IP into that space. They came to dominate this mobile era. RISC-V is really it's really, I think, for this vertical era where people are now building, all systems are being designed this more vertical way. And so you need an ISA that's flexible, it's a standard, people can use in all the different parts of the system. Okay, that's it. So I have 6 minutes for questions. Thank you for paying attention.
Hi there, I'm Tim Matson from Intel.
Hi, Tim.
Yeah, good old Parlab days, I love it. I'm a software guy, I know nothing about architecture. But I have to wonder, when I talk to people who are smart about architecture, one of the things they bring up is the DRAM standards and the way memory is organized, and how that's causing a lot of problems. We need to rethink how memory is laid out and organized. Does that interact with RISC-V? Is there a need for part of your RISC-V group to rethink what if we have to change the DRAM cells? Should there be some memory innovations that go along with this?
I think that is completely orthogonal to RISC-V, but I'll just point out that the reason DRAM is the way it is capacity is king in DRAM. So I'm sorry, but wanting sub-cache line accesses, you're not an important market for DRAM. And the investments are so huge, things won't change there. So I think it's just unlikely. Every boutique DRAM that's ever been tried fails because of volume. So it's just not going to happen. So I'm sorry, but that's the way it is. So economics, business wins, right? Economics. Yep.
Thanks, Krste. Wonderful talk. Software would like the ISA to never change. Won't it have to, for example, not because of memory, which has the beautiful von Neumann abstraction, I give you an address, you give me data, but for example, to support 16-bit floating point or other changes to the data types and the operations that need to be done?
Yeah, so those I consider small changes. So if you look at, when I think about, whatever it is, 50 million lines of code in a Linux distro, how much of that cares about BF16? A few thousand lines. So the point is, it's that tens of millions of lines of code you need to keep going. If you have a few kernels that need a custom instruction, that's fine, that's very manageable, doing all the techniques we all know and love. So whether it's new crypto algorithms, new floating point data types, even new matrix operations, their blast radius is very small in the software base, right? The amount of code they touch and will impact is very small, and that's very manageable. And then we just do this standard evolution we've done for many years to handle those. So I don't see those as a concern.
But will there be, is there a RISC-V version 2 that will eventually arrive to enlarge the basic ISA?
Oh, so the RISC-V, I didn't get time to cover this, but RISC-V is designed as a modular instruction set. So there is a very small base, less than 50 instructions, but that's nevertheless enough to run compile GCC code with dynamic linking and pick and run on OS. And everything else you plug in as modules. And there's a lot of freedom in which modules you include. However, for big distros, they don't want that freedom. So there's what we call profiles, which say, thou shalt have all of these extensions. And the profiles are updated every year or so. The first ones are coming out this year. Plan is to have a major release of a profile roughly every 3 years. And that'll be like a whole bunch of new instructions. But then for distros, they'll be mandated, if you're RVA 23 compatible, you will have all these things and software can rely on them. And that set will grow over time. So you need to accommodate both worlds. The world that needs very stable platform to target, that everybody, all the different vendors will supply, plus the highly customizable ones. And you need both of these things. Actually, let me, so this is something people get confused, the difference between fragmentation and diversity, right? So fragmentation is a bad thing. That's when you do the same thing 2 different ways, right? So left-hand drive, right-hand drive. Like, why didn't we just pick one? Like, why do we need, like, all it does is add cost and expense to car manufacturers, right? Diversity is a different thing. I have a different problem. So if I want to go cross town and pick up some groceries, bicycle is a great way to do it. If I want to carry 500 people over an ocean, I don't want a bicycle. I want a jumbo jet. But I don't want to mandate everybody uses a jumbo jet to get their groceries, right? So that modularity gives you support for that diversity. But we make sure that there's only one way of doing, say, bfloat 16. There's just one standard way that ends up being the standard. When you're doing that way, you do it this way. But you may not want to do that, and that's fine.
We do have one question from online. In your opinion, Doctor, when do you estimate the inevitable to occur? Is it a decade or less?
So when I assume the what will occur?
When the inevitable.
Inevitable. So it depends on which market you're in. I think a lot of embedded microcontrollers is already kind of happening. I think in other areas, it's being accelerated by current events. So I always think it's further out, and events always seem to bring it closer and closer in. So I think in mobile handsets, it's a few years away. I think in servers, it's a bit further away, maybe. Most other areas are already, people are looking this way.
We can take one last question.
Hi, thank you. HPC, particularly scientific computing, tends to have highly specialized applications, but for the last few decades has relied on largely general commodity hardware that has to support many use cases. So could you talk about how the RISC-V ecosystem may provide more flexibility and competition, customization, particularly for trade-offs of reliability, power, and performance?
Yeah, I think that's a problem that won't be solved by RISC-V. That's a problem of economics, and it's just going to get worse. So the advanced technologies cost even more to develop, so you need even better case for building them. I think the one thing that might help HPC is chiplets, in that you can more closely couple a custom accelerator takes less money to develop than doing the full silicon. But in reality, I think the problem you're seeing is one of economics. HPC is just not a big enough market to justify custom silicon. And as the cost of custom silicon goes up, it's even less likely you'll get custom silicon. So chiplets, I think, is the one hope for getting HPC-focused systems done at reasonable cost. I mean, basically, government subsidized. There's no real business. It's government subsidized at scientific supercomputing. And to make it amenable to, I think chiplets is the near-term possible relief valve to enable better things to happen for HPC.
Thank you very much. Let's thank our speaker one last time. Thank you very much for attending the session this morning, and I hope you enjoy the rest of SC22.